We'll wait for a couple minutes to let a few more people join. All right, let's begin. So we won't have first couple announcements. We won't have a tutorial today. I uploaded the tutorial questions which are based on first and second laws of thermodynamics. And I have already shared all the thermal physics related slides. So kindly go through them and then think about those tutorial questions and we'll take them up next week. And in the meantime, I will be giving another homework later tonight, which will be due the Monday after next. And this will be uh, kind of giving you some hands-on experience with working with the Gibbs principle and its consequences. Okay. All right. So let's get started. So in the last class, we set up the Gibbs-Boltzmann distribution, and the way we derived it, which was on the lines of what Boltzmann himself did, we we computed the statistical multiplicity of a simple system, and we took the logarithm of that statistical multiplicity and we maximized that by putting two constraints. One is that the total energy of the ensemble is a constant. That is, if you take a large collection of systems which comprises sort of a universe and there is nothing other than that large collection of systems, then the total energy of the ensemble will be conserved and the total number of systems in the ensemble is also conserved. And using these two, we derived an expression which said that the probability that the system, let us say the system has states A1, A2, so on. Okay. And the probability that the system has a state AI is proportional to e to the power of minus beta EI, where EI is the energy of the state AI. Okay. And then we said that it is some normalization factor times e to the power of minus beta EI. And this normalization factor can be computed using the condition on probabilities that P of AI summed over all states AI should be equal to 1. Okay. This is the idea of the Gibbs principle. And then we started looking at how now one very important feature of this principle is that the probability of the system being in a particular state is a function of the energy of that state alone. Okay, this is an important result of what we just looked at, and there are consequences which are quite interesting. A, a very immediate corollary is that all states of a system which have a particular energy, let us say E, okay, all states of a system which have a particular energy E have the same probability. Okay, they have the same probability. Now what this means is, if you have, say, let us say uh, let us say we have m states, say m states, or m is usually a function of E, okay, m of E states have energy E, then the probability that the system has energy E. Now, this question, the probability, what is the probability that the system has the energy E, is a different question from what is the probability that a system is in a particular state with energy E. Okay. So the Gibbs principle gives you a straightforward answer to the second question, which is what is the probability that a system is in a particular state with energy E, and the answer is it is proportional to e to the power of minus beta E, where beta is 1 by kBT, a function of the temperature. And now what we are asking is, let us say there are m of E states where m stands for multiplicity. Okay, m of E states, each of which has an energy capital E, then the probability that the system has energy E will be proportional to quite simply because each state has a probability e to the power of minus beta E, and all these m of E states, the probabilities will add up. Because if the system is in a particular state, it cannot be in another particular state, meaning these are mutually exclusive events. So the probabilities for all these will add up. And what you get is usually the statistical multiplicity times the energy. Okay, so this statistical multiplicity is also called degeneracy. So so to degeneracy in a strict sense means uh, different states of a system have the same value of some parameter or some physical observable. Okay, so this is the meaning of degeneracy usually in the strictest sense. In the
Excuse me,
most,
sir.
yeah,
Uh, Sir, how do we ensure that me into e raised to minus beta e is less than or equal to 1?
we don't have to ensure that is always taken care of, because the condition is that sum over all E, m of e power minus beta E times some normalization constant, okay, should be equal to 1. This
Uh,
normalization will take care of that.
yes, sir.
That's why I did
Sir,
not write equal to, that's why I wrote it as proportionality.
mhm. Yes, sir. Sir, and is this correct? Like you've written, then the probability that the system has energy E, or should it be that the probability that the system exists in such a state?
No, 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 that is precisely the difference. When I say that the system has when I ask the question what is the probability that the system is in a particular state, say AI, then you can, from Gibbs principle, you can immediately say that it is e to the power of minus beta ei, where with some normalization constant, of course, where ei is the energy of the state ai. But what I'm asking here is, what is the probability that the system has the energy E? Then the system could have an energy E while it is in state, say A1, then it is even A2 can have the same energy E. Then you have to add the probabilities for each of these states. That is where this multiplicity comes in.
Yes, sir. Yes.
Got it? And in
Yes.
terms of this now, this is the overall unit probability condition. The total probability has to be 1. So from this you can say that n should be 1 by summed over e, m of e to the power of minus beta e, right? Because
Yes,
each
sir.
probability will have the same. That is how you ensure that the probability. So then the probability that the system has an energy E is basically m of e to the power of minus beta e by summed over all e to the power of minus beta e m of e, which is decidedly less than 1 when all these are positive numbers. So 0 less than or equal to this, less than or equal to 1. That is the idea. Is that clear?
Yes, sir.
Yeah. Now, degeneracy in general refers to different states of the system having the same value for a particular physical observable. For example, you can consider a particle moving to the right with a velocity v and a particle moving to the left with a velocity v or minus v. They will have different momenta, but the kinetic energy of these two is pretty much is the same, right? So as far as kinetic energy goes, these two are degenerate states. If you now have momentum into consideration, if you take momentum into consideration, then you can distinguish these two states, and that then you say that, so if you have two particles of mass m moving like this, kinetic energy is degenerate, momentum is not. So if you specify only the kinetic energy of these two states, you cannot separate them. That is precisely what we are doing here. As long as we ask the question, what is the energy of this of a particular state, and we don't care about what all other physical observables are for that particular state, then in the energy variable, these states can become degenerate. And since the Gibbs principle says that the probability depends only on energy, you get this multiplicity factor. All right. And usually from this little example of kinetic energy and momentum, the question of degeneracy is a matter of which observables you are taking into account to describe the state of the system. Very often, I'm not saying always, very often degeneracy is a question is something that arises when you ask a question as to what uh, a particular value of a particular observable is. But if you consider another observable, for example here momentum, then so in this case the momentum value lifts the degeneracy of the energy values. So if you take only the kinetic energies into account, these two states are indistinguishable. But if you now consider momentum, you can clearly say that, okay, this is a right moving particle with energy half mv squared. This is a left moving particle with energy half mv squared. Okay. So you usually need to specify other variables in order to lift this degeneracy. But here, the probability depends only on energy anyway. So you get this multiplicity factor. Now I wrote this expression as a summation over all energy, summation over all energies. Usually energy is a continuous variable. Okay. So what we energy is, at least classically, energy is not a discrete variable. So we need to define a probability density. Okay. We cannot actually define the probability that the system has an energy E, but in fact we have to define a probability density that the system has an energy E. Then this probability, okay, so energy is a continuous variable. This implies from P of E, we have to actually go to rho of E, probability density function. Okay. And then we can define the probability that the energy is in a range from E to E plus dE as rho of E dE is the probability that the energy of the system is in a range E to E plus dE is, now you can write it as rho of E dE is usually G of e to the power of minus beta E dE, where this G of E is now called the density or the energy density of states. Okay. And this is a very, very important function in all of physics. Once we discuss black body radiation, or in the process of discussing black body radiation, we will actually spend some time on this energy density of states. But this is the context in which the energy density of states arises. Basically, if you think of a discrete energy spectrum, when I use the word spectrum, I mean energy is a variable, and say the values of the energy, the possible values that energy can take, that is the spectrum of energy. And M of E, the first time I wrote it as the statistical multiplicity, I assumed energy was a discrete variable. And you will see that in quantum mechanics, this is often the case. But classically, in general, or even quantum mechanically, under certain approximations, energy is treated as a continuous variable, in which case we cannot define a probability that the system has an energy E, which will be just zero, but we can define a probability density function. And in terms of the density function, a probability that the energy is between E and E plus dE can now be defined as rho of E dE is G of E to the power of minus beta E dE. Okay, and then the normalization condition essentially becomes integral G of E dE. Okay, sorry, this is proportional to, and then there will be some normalization. Let us say that normalization is capital N. Okay, and you just use the same principle, integral G of E dE e to the power of minus beta E times N equal to 1. So that normalization constant now becomes 1 by integral dE G of e to the power of minus beta E. This expression that we wrote here is exactly equivalent to, so when we wrote summation over all states I e to the power of minus beta EI, this is in the discrete limit. This goes to integral dE G of e to the power of minus beta E. So whenever you take a summation over all these, I are distinct states of the system. Okay. These I are distinct states of the system. For example, a right moving particle with velocity v and a left moving particle with velocity v are distinct states of the system, but they have the same energy. So when you go from a summation over all different states, this is the more fundamental expression for the normalization or the denominator of the normalization constant. When you convert the summation into an integration, it should not be done merely as integral dE. You cannot just go to integral dE. Instead, you should include this density of states. It's a natural consequence of going from a summation to an integration. Is this point clear to everyone? So in statistical physics or in thermal physics, when you go from a summation over states to an integration over energy, you will always have this density of energy states factor g of E come into the integral. This is often, this is a very common mistake that students do in the initial days. They forget this g of E factor. Okay. And this g of E has very, very important consequences, some of which we will discuss later in the course. All right. So this is about the density of states. Now let us look at, we also wrote another expression for this Gibbs probability. So let us say you have a mechanical system. Any mechanical system. When I say a mechanical system, a system that moves, that has constituent particles that move according to the laws of classical mechanics, basically Newton's laws. Okay, the forces can be very different. For example, there could be Coulomb's force or gravitational force between the particles. It doesn't matter which force, as long as the constituent particles move about with certain velocities and forces depending on the positions of the particles. Such a system is a mechanical system, and many systems that we look at have an internal description which is a mechanical system like that. Every mechanical system, okay, which has with n constituent particles or constituent particles, let us say, is described in 3 dimensions. That is an important detail here. In 3 dimensions is described using 3n coordinates and 3n momenta. Okay, and we call these coordinates x1 to x3n and p1 to p3n. Therefore, the dynamics or the dynamical evolution of the system takes place in a 6n dimensional. What is this space called? Phase space. Okay, this the 3-dimensional space that we talked about is just the coordinate space for one particle. If you have n particles, there are 3n coordinates that you need to specify. Okay, and if you also and each of those particles will also have a momentum, which is also a vector with 3 components. So there will be 3n momenta. So 3n coordinates and 3n momenta. That makes a 6n dimensional phase space. So the entire system, let us say an ideal gas in a volume V. Okay, this can now be described using by specifying the coordinates. Can be described in phase space using 3n coordinates and 3n momenta, or x1, x2, so on, p1, p2, so on up to p3n. A point in 6n dimensional space. And as this gas, as the, this is, so this description, okay, such a description using x's and p's is called a microstate. Okay. Now remember that we have very simply written this as 3n, but n is of the order of Avogadro's number, which is 6.023 times 10 to the power of 23. It's an enormously large number. And in principle, to even write down these coordinates, just to take a picture of this, entire gas, and to record the coordinate of every particle, forget even the momenta, to take a static picture and to record the coordinates of all these particles is a humanly impossible exercise. Okay, so while we have written in principle a microstate like this, it is very clear, it's very intuitively clear to us why we need uh, a description in terms of a macro state. Okay, a huge number, of microstates, a huge number of microstates together or on average describe one macrostate. Okay, so because of this averaging effect over very large number of microstates, a macrostate becomes a more feasible description. If you say that, okay, this gas has a pressure P, a temperature T, and a volume V, that completely describes the system, not in the sense of a microstate. We have hidden all the information of the microstate into these statistical variables of pressure and temperature and volume, the macro variables. Okay, macrostate is described using macroscopic variables, which we already talked about in thermodynamics. Okay, now Gibbs principle applied to a mechanical system, and by mechanical system I mean that the energy is now a function of all 6n, in principle a function of all 6n coordinates and momenta. Okay, then since x's and p's are continuous variables again, we define a density function rho, that the system is at a point at probability density. Okay, that the system is at a point x1 to x3n and p1 to p3n in the phase space, and the probability that the system exists in a small volume, an infinitesimal volume d omega of this space is given by this, where d omega is, it's a very common notation to write it as d capital omega, where d omega is nothing but dx1, dx2, so on up to dx3n times dp1 times dp3n. Okay. And this probability can now be written d omega equal to e to the power of minus beta e of x1 so on up to p3n d omega divided by integral. When I write 3, I usually mean multiple times d omega, this integral and e to the power of minus beta e x1 to p3n. This is the most general expression for any mechanical system. And how many integrals are there here? Can somebody tell me? Can somebody tell me how many integrals there are in that? I mean, I just want you to appreciate that if you really want to do this calculation, even for the simplest of systems, it can be done. But any more complexity and you are in, these are not so trivial. None of this is trivial conceptually, because we are writing it quite simply. This multiple integral here has 6n integrals, and n is of the nature of the order of Avogadro's number. So at the very face of it, when we look at this integral, which is so simply written on a piece of paper, it looks innocent. But if you stare at it for a few seconds and realize that there are 10 power 23 integrals in the denominator, you quickly lose hope. But all is not so hopeless. In fact, we even bother to write this form because for most systems, this can be analytically computed. Not for most systems. For the simplest of systems, we can analytically compute it in a rather trivial fashion, as we will show in a minute. And the consequences are very far reaching, and most complex systems can in principle be broken down into such, you can at least formulate the problem of a complex system and try to reduce it to a more familiar form and then use these results. Okay, so that is the usual strategy that physicists take everywhere. Not just physicists, I mean anybody who is into problem solving as a I don't mean JEE problems. Yeah, Soham, you have a question?
So do we assume here that each state has a different energy?
We are not assuming anything. In fact, we are assuming that no, we are not assuming that. There could be an enormous number of states with the same energy. We don't care. This is an exact expression which comes from our analysis. In principle, this is the correct expression in phase space, where d omega is the volume in phase space.
Sure, but shouldn't it be me into e raised to power minus beta e d omega? Because we are considering the probability of the uh, system to be in a particular
Not
state. And
necessarily, right? For example, I'm integrating. Okay, that's a very good question. The answer is no. We are not really, we don't have to consider the energy, because the way I described the energy here is in terms of a particular set of coordinates. And what is this? These x1 to p3n in the numerator. Okay, they are some particular coordinates.
okay, so yes, I got
You,
it.
you get the question? Yeah, sorry, you get the answer.
Yes, sir.
We are computing the probability that the system has a particular value of all the coordinates and momenta, and that's where you get this expression. And in the denominator, you are only normalizing it using the same description in terms of the phase space variables. It turns out that most of these systems, as you very well know, for example, Let us now apply this to an ideal gas. Let us apply this. Apply this to an ideal gas. Now for simplicity, let us consider a monatomic gas. And when I say ideal, we don't include any interactions between the molecules. Any collisions that happen between these molecules of the gas, that is still okay. We don't care about those, and we assume that those collisions happen rather rarely, because most real gases behave in an ideal fashion only when their densities, the number per unit volume, is rather low. So that is the approximation in which an ideal gas works. And we take a monatomic gas. What is the energy function of an ideal gas? Half m1 v1 squared plus half m2 v2 squared plus so on plus half mn vn squared. Okay. Now, in general, v1 squared is the velocity of one particle. So that can be vx1 squared plus vx2 squared plus vx1 squared plus vy1 squared plus vz1 squared, etc., etc. So the vith particle will have three coordinates like that. So if there are n particles, this summation here, and we can also write this in terms of the momenta, noting that pi is m, let us say pxi is mvxi. Okay. So noting this, we can write this as px1 squared by 2m1 plus py1 squared by 2m1 plus pz1 squared by 2m1. All these three correspond to the kinetic energy of the first particle, plus like that, and there are n such terms in this summation, one for each particle. Okay, so these are the 3n. Therefore, 3n terms in the summation. Note, E for an ideal gas does not depend on the coordinates. That's a major simplification. There is no potential energy anywhere. So whenever we say potential energy, it is something that depends on the coordinates. So the forces acting on the particles depend on the coordinates. We don't have any such thing here. So the total energy of the system for an ideal gas is only a function of the momenta. And let us now try to compute. So let us write down what is the probability that the system has an energy, sorry, the system has coordinates x1 to x3n and p1 to p3n, and assume m1 equal to m2 equal to so on equal to mn equal to some mass m. That is, all the masses of the particles are identical. That is, these are all particles of the same gas or same species. Okay, this makes our calculations simpler. So let us now compute the probability that the system has values for the coordinates and momenta in a certain small infinitesimal volume of phase space. And we know that that is nothing but e to the power of minus beta. And what is E here? It is, I will now simply write it as p1 squared by 2m plus p2 squared by 2m. You should understand this to mean the three coordinates. Sorry, just hold on for a second. I'm getting a phone call. Hello. Yeah. So we will have in principle uh, a term like this from the exponential. And then of course we should not forget the d omega part. So we'll have dx1 so on to dx3n and dp1 so on to dp3n in the numerator. And in the denominator we have the normalization factor, which I will write it as this, and then dx1, dx2 so on up to dx3n, and then dp1 so on up to dp3n, and the same factor again. Okay, and now we have e to the power of minus. Let us try to work this out. At least put it in a form which then we have the dx3n and then dp1 to dp3n, and the denominator. Okay, I can, this integral here depends only on the momenta. So the volume integral doesn't play a role at all. So what I can do is, from the basic rules of integration, I can take out the volume part and right, there is no problem. But this one here is very easy, because integral dx1 dx, let us say dx dy dz for one particle over the entire volume V. Can somebody tell me what this is? Integral dx dy dz. What is it? It should be equal to V, the total volume, right? The
So
coordinates,
for one,
sorry.
sir, for one particle, what do you mean by that?
Yeah, yeah, I'm coming to that.
Instead of
That's a good point. I just want to clarify what we are doing here. We are, forget about one particle. These are dx dy dz. The subscript 1 stands for the first particle, right? And subscript 2 for second particle, and so on to subscript n for the nth particle. There are 3n such differentials because of the three directions. Let us say this is the x direction, this is the y direction, and this is the z direction. Now x goes from, let's say, minus L to plus L, and similarly it's a cubical volume. So y goes from minus L to plus L and z goes from minus L to plus L. So integral 0 to, or let us say 0 to L, 0 to L. Yeah, x goes from 0 to L, y goes from 0 to L. So integral dx dy dz is basically integral 0 to L dx, integral 0 to L dy, integral 0 to L dz, which is nothing but L cubed, which is the volume of the cube. So each triplet of such space integrals contributes one volume, and there are n such triplets. So this factor here in the denominator will just give you, so rho of x1 so on to p3n d omega will be, this is e to the power of beta, e to the power of minus beta capital E p3n d omega divided by v power n. Okay, v power n integral e to the power of minus beta p1 squared by 2m plus so on to p3n squared by 2m dp1 dp2 so on up to dp3n. We have already simplified the denominator significantly, but again this n is of the nature of the order of Avogadro's number. So all these expressions are easy to write, but if you just imagine their magnitudes, they are enormous. Now consider this other integral. This is also quite trivial because P1 is the momentum Now we have confined the gas in a volume V, so the coordinates are limited, but we did not say anything about the momenta. In principle, the momenta can be arbitrarily large. Even within a small volume, a particle can move enormously. There is no problem. So P1 goes from minus infinity to infinity in principle. And similarly, every Pi. And the fact that this exponent is a summation over individual Pi's, you can write this as e to the power of minus beta Pi squared by 2m product over all I. So I hope you guys are familiar with these symbols. When you write sum over I, you write sigma E, sigma I, and product is this big pi with I as the subscript. Okay. So this expression here can be written as a product. So the integral over this multiple integral over dp1 to dp3n of this, you know, uh, p1 squared by 2m plus so on up to p3n squared by 2m. This very simply becomes a product over integrals, each of which is over only one variable. Okay. Now this integral here is one of the most important integrals that you should know in physics. This is a simple Gaussian integral. Okay, which can be evaluated quite easily. And it is very simple that integral, okay, e to the power of minus x minus mu squared by 2 sigma squared. A Gaussian is usually specified using two parameters. Okay, so sigma root 2 pi dx. This integral has a value of 1. Therefore, integral dx e to the power of minus x minus mu squared by 2 sigma squared is equal to sigma root 2 pi. This is a standard Gaussian integral which you should remember because we will encounter this almost everywhere in physics. And we already talked about why the Gaussian function is an important function, right? I mean, we talked about the large law of large numbers and the central limit theorem, law of large numbers. So this Gaussian function plays a big role in physics. And how does this Gaussian function look? So if you have some mu, this mu is called the mean value and sigma is the standard deviation. This Gaussian function looks something like it's the usual bell curve that most UGs dread when people do relative grading. This is the curve that people use for assigning your letter grades. Fortunately, we are not doing that in this, in this course. But this is the basic idea of a Gaussian. This is how a Gaussian looks, and these tails here asymptotically go off to 0 and rather fast because they fall off as e to the power of minus x minus mu squared by 2 sigma squared. They fall off very fast. Okay, so I kind of magnified it to show you the sigma, but in principle this is a very sharply peaked curve around mu. Okay, so this integral can be done very easily. So integral of x minus mu squared by 2 sigma squared is sigma root 2 pi. Now let us just do integral dpi e to the power of minus beta pi squared by 2m. Now this is the integral we have. All we need to do is integral dpi e to the power of minus pi squared by 2m by beta. And immediately we realize by analogy, by comparing these two expressions, that mu is 0 and sigma is square root of m by beta, right? Is that clear to everyone? And therefore, this integral dpi e to the power of minus beta pi squared by 2m is nothing but square root of 2 pi times sigma, which is square root of m by beta. That's it. And we have n such, we have capital N such or 3n such integrals, right? Therefore, product of I going from 1 to 3n integral dpi e to the power of minus beta pi squared by 2m is nothing but this factor raised to the power of 3n. So square root of 2 pi square root of m by beta to the power of 3n. Is that clear? So now we can write the row of x1 to x3n comma p1 to p3n is nothing but e to the power of minus beta divided by, we have in fact evaluated the normalization constant exactly. So we have v times n, v power n times square root of 2 pi square root of m by beta power 3n. Any questions on this? Sorry, I should have specified the limits. This limit is from minus infinity to infinity. Any questions? I want to pause here for a second and see if you guys have any questions, because we did cover, perhaps I have, as I teach this course, I have learned that since you guys anyway know first law of thermodynamics and all these things from earlier courses, the next time I teach, I'll be starting with, I'll do a quick review of first and second laws in maybe 2 lectures and then move on to this part, which is the crux of thermal physics, in fact, which I'm pretty sure you would not have studied. Did you study all this earlier?
No.
The Gibbs-Boltzmann principle and
No, sir.
okay. Yeah. So thanks to your feedback, your next batch will benefit. Unfortunately, you guys uh, will not reap all the benefits of this, but sure, that is how any feedback works. So any questions on this, on what we have done this, what we have done here? What we have done is a massive simplification, at least for the case of an ideal gas. Okay. Now, once we have this tool in our armory.
Excuse me, sir.
Yeah.
So even if it wasn't an ideal gas and all the molecules weren't identical, we could still have written the latter term as the product of square root of mi, where I is 1, 2, 3, and
Sorry.
sir, even if all the molecules in this gas weren't identical,
Huh.
we could still have written the denominator as v raised to n into a product of root of 2 pi mi upon beta.
Oh, ideal gas doesn't require the masses to be identical. That is a special condition that we took for one particular species of an ideal gas. When we say ideal gas, we usually mean there are no interactions between the particles and therefore there is no potential. If the energy, okay, if the energy depended also on the coordinates, we could not have easily written this v power n, because that factor came only from The fact that the energy did not depend on the coordinates at all.
Yes, sir. Yes, sir.
Yeah. Okay. So now let us try to apply this. Now, what we want to do is, so this is the probability density function. Now that we have the probability density function, I should write the d omega here. That's an important thing we should not forget. The once we have this probability density function, every every quantity pertaining to this system can now be computed the average value. Okay, the average value, let us say there is a quantity A, which again depends on x1 to x3n and p1 to p3n. So usually any quantity that depends on the coordinates and momenta of a particular system is is a dynamical variable for that system or a physical observable. Okay, like energy, angular momentum, they all depend on the coordinates and momenta. Okay, so for any variable A, we can now compute the average value of A, which is usually denoted using this angular brackets. Okay, and that is equal to integral A of x1 to x3n p1 to p3n times the probability rho of this times d omega. Make sense? In probability theory, that is how we define average values. They are also called expectation values. This is for any variable, any observable A, which depends on x1 to x3n and p1 to p3n. Now let us compute the average value of the energy itself. What is the value, average value of energy? I will not compute this. I will actually write it. I will say that it is E of P1 to P3n because for an ideal gas. Okay. For an ideal gas, this value will be P1 to P3n times the probability density, which is e to the power of minus beta P1 squared plus so on to P3n squared by 2m. For simplicity, I'm assuming that d omega, which is the integration element, divided by integral d omega e to the power of minus beta p1 squared plus so on to p3n squared by 2m. Yeah, this is the expectation value of energy, and we know that the denominator can be easily evaluated by 2m. Okay, times e to the power of minus beta p1 squared so on up to p3n squared divided by 2m times dx1 so on to dx3n and dp1 so on to dp3n. Sorry, the terms are getting longer and longer, so and the denominator looks like v power n square root of 2 pi m by beta all under root power 3n. Now this factor is constant for everything, so I'll just bring it out. I'll say it's 1 by v power n square root of 2 pi m by beta power 3n, and in this square brackets, flower brackets here, I will have an integral. Okay, an integral that goes as p1 squared 1 by 2m I can take out because this factor comes out. It's a multiple integral again. P1 squared by 2m plus P2 squared by 2m. Sorry, I've already taken out the 2m. Plus P3n squared times e to the power of minus beta summation over by 2m, and the integration variables are dx1 to dx3n and dp1 to dp3n. Now that we have written down the integral, this three n, this again, since the energy doesn't depend on the coordinates, this energy, this coordinate part separates out, and we can write it as v power n times, okay, because that comes out as a product, v power n by 2m, that comes out as the common factor. And now we only have an integral over the momenta, and the integrals are not so, sorry, I should not write that by 2m again. P1 squared plus P2 squared plus so on plus P3n squared times the probability now. That is already, we are slowly chipping away the difficulty of this integral. So v power n goes away. So that now becomes 1 by 2m square root of 2 pi m by beta power 3n, and we now have a summation over I integral dpi, okay, p1 squared. We should be a little more careful in writing this. Yeah, correct. Yeah, pi squared. Yeah, correct. Integral dpi times, okay. So there will be a summation over integrals, and there will be, sorry, let's write it carefully. So there is a pi outside here, and there is a pi in the exponent. So that pi will also be pi squared by 2m. That is also here. And then there will be a product of all other integrals dpj, j not equal to I, e to the power of minus beta p j squared by 2m, right? And this is the one that is summed over. Each term in the summation will have a structure like this. And we know exactly how to evaluate this. We evaluated it here. It's going to be summation over I integral dpi e to the power of minus beta pi squared by 2m. I'll finish this and we'll conclude, okay? This is nothing but square root of 2 pi m by beta power 3n minus 1. Agreed? Does everyone here agree?
Yes, sir.
One pi came out, so that's the minus 1 that came out here. And all this integral is basically the simple Gaussian integral multiplied 3n minus 1 times. So we have this divided by 2m square root of 2 pi m by beta power 3n, and we can now
Excuse me,
write,
sir.
sorry.
Uh, Sir, shouldn't there be a pi squared in that term?
Oh,
Which you have
very good. Yes, yes, yes. After all, that is, yeah, yes, we should have a pi squared there. And since this is a common factor, we can now, and what you get is 2 pi m by beta in the denominator. Now this is already looking very attractive because we have a summation of terms, each of which is equal, because each integral goes from minus infinity to infinity. So these dpi's are basically dummy variables, We are integrating over the full range and you are adding 3n of those integrals. This capital N, which is of the nature of Avogadro's number, is no longer in the exponent, which is a very formidable place for it to be. It is now in the product. So we now have this numerator here simply becomes capital 3n, meaning 3 capital N, multiplied by the value of this integral. Integral minus infinity to infinity dpi squared. There is no I anymore, so I can remove the I because I have, by writing the 3n outside, I have considered all i's. dp p squared e power minus beta p squared by 2m divided by 2m square root of 2 pi m by beta. We are right there. We are very close to the final answer. Okay, so this is the average value of energy. We are very close to the final answer now. If only we could evaluate this integral. Okay, if only we could evaluate this integral, we are in a very good place. So let us see integral dp. So we can now forget all other terms, focus our attention on this integral. We don't know how to do this, but what we know is the following. We know integral dp e to the power of minus beta p squared by 2m. Okay, this is equal to square root of 2 pi m by beta. We know this. This looks very, very similar. What is this? If we know this, how can you compute that? So let us leave that as an exercise. This is a evaluating Gaussian integrals is fairly standard. I want you to figure out a way to go from here to here. We will anyway take this up as the first thing in Monday's class, and we will then by doing this integral, we have solved the full problem of computing the average energy, which is the internal energy of an ideal gas, which is a very important quantity for this course or for
Excuse me.
any course on statistical physics. Yes, Soham.
Sir, how did we assume that all the PIs have, like, the PI does not matter? The momentum or the
Oh,
integral would be
oh,
the
oh,
same
oh,
for
oh,
every.
oh, oh. It's simple like this. Let us say I have x squared e power minus beta x squared dx. Okay. This is equal to integral minus dy y squared e power minus beta by 2m y squared, right? It doesn't matter whether I write this as x or y.
Yes, yes, sir.
It's a dummy variable. Now, if I take a summation over different, over different dxi's, and if this summation has 3n terms, each of these will be equal, and you are adding 3n of those equal terms. So this will just be 3n times integral minus infinity to infinity dx of whatever function you are considering, as long as that function is only of xi.
Yes, sir. Got it.
That is what we did. Any other questions?
Sir, and for the answer to the exercise, probably we can use integration by parts 2 times.
There are quite clever ways of doing this. So yes, you have to use integration by parts, but in a sort of clever way. Think about it. We will do this on Monday anyway, but it's a nice weekend exercise for you to uh, brush up some of your integration skills, which in my observation, as students grow up, the first casualty is their integration skills. They end up using Mathematica. I want you to do this without using Mathematica, of course. They start using Mathematica and all these tools, and ultimately you end up incapable of solving any integrals later in your life. So assume a world without power, an apocalyptic situation where you are stuck without Mathematica, and try to solve this integral. All right. So with that, let us conclude today's lecture. We will start, we'll again meet on Monday morning, and we have set up all the ingredients to discuss, you know, black body radiation. So next topic will be black body radiation, and we are off into quantum physics at that point.
Thank you, sir.
Okay. I will then see you on Monday.